In Cycle 2, Lesson 9, we're going to keep working on combining functions. Last lesson we did adding and subtracting functions. Now we're going to multiply and divide them. In other words, products and quotients. So let's start just by jumping in with a couple of functions defined by sets. There's function f, here's function g. They're again defined as a set of points. Remember when we added functions, we found x coordinates were the same and added the y coordinates. When we were subtracting, we found x coordinates were the same and subtracted the y coordinates. If we couldn't find an x coordinate that was the same in both functions, for example, here's an x coordinate of -2. There is no x coordinate of -2 in this one. So if that's the case, we can't combine on those points. We can only combine the ones where they actually do match up. The other thing that we may have noticed I didn't talk about, but let me point out now, when we were adding them, it didn't matter if I added f plus g or g plus f. In other words, if I was to add these 2 points together, 4 plus 2 on the y-coordinates gives me 6, but 2 plus 4 also gives me 6. Order doesn't matter. That's actually called being commutative. If I subtract, well, let's keep it on these ones. If I was to do 4 minus 2, if I was to do f minus g, I'd get positive 2 for my y value. But if I was to switch the order around and do g minus f, I'd get -2 for my y value. That means those are not commutative. And we're going to see that extends to multiplying and dividing. Multiplying is commutative. It doesn't matter what order you multiply things and you're going to get the same answer. Dividing is definitely not. If I divided, circle these one more time, if I divided 4 by 2, I would get positive 2. If I if I divide 2 by 4, I get a half. So the order I divide in is going to matter as well. But you probably can already see where we're going with multiplying and dividing because it's exactly the same idea. So I can combine these two, and I'm going to do that. First I'm multiplying. Keep the x the same, multiply the y. Did you expect 8? Probably. And I can skip over the -2, but the 1's match up. And I can skip over 3, but the 4's match up. So my multiplying is going to get me 112 and 4 and -16. The 12 comes from doing 6 times 2, and the -16 comes from doing 8 times -2. Dividing, again, not commutative, order matters. So I'm dividing f by g in this case, keeping the x's the same. So 4 divided by 2 is 2. 6 divided by 2 is 3. 8 divided by -2 is -4. Okay, we can also, just like we did before, sketch graphs of things, or combine them, let's say, using sketches. We want to find key points again, though. So 0, 3, I think this is the exact same one I was looking at before, isn't it? From last lesson, if you remember. Here's the points on the blue graph. Here's the points on the red graph. And this time I'm looking to divide. And f was the blue graph, and g was the red graph. So if I'm dividing f by g, I want to go along at all the different points and divide the y-coordinate by the y-coordinate of the blue by the y-coordinate of the red. So I would get, when I do that, let's do this in green. So for at -8, I'm going to divide -3 by +1, and I'm going to get -3. So I'm going to get a point at this, at -8, -3. Here, I'm going to divide 0 by 0, which doesn't make sense now, does it? We can't divide 0 by 0, so let's just make a note of that. At x equals -4, f over g, function f divided by function g, is 0 over 0. Does not exist, right? Undefined. So for now, let's just put an open circle there. I know we've done vertical asymptotes up to now, but I think we're going to see that we don't want a vertical asymptote in this case. But let's carry on. At the next one, we've got positive 3 divided by negative 1. Oh, it's a negative 3 again. Oh, and I guess, why did I put an open circle here? Good question. Why did I put it at negative 3? Let's not put it here for now. I'm thinking ahead. So I'll just totally ignore what's going on at x equals negative 4 for now and just look at the other ones. Though at the next one here, sorry, I put this in the wrong place, messing everything up there. Fix that point. At positive 4, I'm going to have 6 divided by negative 2. That's also going to give negative 3. And then for this last one, I've got 9 divided by negative 3, which also gives negative 3. So it appears that we end up with a straight line as we go along here. Interesting. We can probably assume it's going to keep going on forever to the right and forever to the left. But what happens as I get closer and closer to negative 4? Well, we could try different points. If you take a look at the function f, the blue one, it's getting, as I move this way, it's getting less and less. And as I look at the red one, as I move this way, it's getting less and less as well, but from the negative side. You could try some points if you wanted to, and see that even if I was to pick different points, I'm still going to get negative 3. So let's estimate some points right here and here. That looks like, could it be maybe 0.9 and maybe on this part and maybe negative 0.3 on this one? Well, 0.9 divided by negative 0.3 would still give me negative 3. So I'd still get a point here at negative 3 by combining these ones. Now I'm estimating, of course. It may not be those exact values. But I can tell you that they are all going to keep going to be negative 3 as we keep moving this way. So if we're defined as negative 3 all the way up until we get to negative 4, and the same thing's going to happen on this side, but we can't include any point at negative 4, that's why I jumped the gun and put an open circle here. We're going to keep getting closer. We can get x values that are closer and closer to negative 4, but I just can't define it actually at negative 4. So the open circle means don't include it. That's called a hole. So we graph it like that. You can see why it's called a hole. It's not an asymptote because the graph doesn't have asymptote behavior near it, but it definitely isn't defined at that point either. So it's just a hole. And so that hole is infinitesimally small. I could have an x value of negative 3.99999 with as many 9s as you want to throw on there, and I would still have the y value of negative 3. But the second I get to negative 4, it's undefined. Product and quotient of functions. Okay, so we're just going to look at a couple of these. So if f at x equals x plus 3 and g at x equals x squared plus 8x plus 15, these are our two different functions. We want to combine them, and this time we want to multiply them. So we're just multiplying these two things together. When we're dealing with equations, we've actually done this before. We just plug in x plus 3 for f at x. We plug in everything x squared plus 8x plus 15 for g at x. And we know how to expand polynomials, right? I'm going to multiply each term in the second bracket by each term in the first bracket. So I'm going to end up doing 6 multiplications. And I'm going to end up with x cubed plus 8x squared plus 15x. That comes from the first 3. Then I go back and multiply everything by 3. 3x squared plus 8x plus, messed that up a bit, didn't I? Plus 15 should go here. But this should be plus 45. Combine my functions. Put all my x cubes together. I've only got one x cubed. But I've got 2x squared, so I could add those together for an 11x squared. I've got 2 x terms, so I could add those together for 23x plus 45. And then we can graph it. I don't expect you to know what this looks like yet, so we'll go to Desmos, our old friend. What did I say? 23. Oh, I made a mistake. My mistake. I'm sure you caught this as I was going along, but this should not be an 8x. This should be a 24x. So sorry. So when I add those together, I actually end up with a 39. And here is our graph. So it's got x-intercepts at -3 and -5. It's got a local maximum at -4.3 and 1.1. This scale is so small, so very small, that we're not going to see it very well. The y-axis, that is so small. And the y-intercept, alright, if I want to see that, I guess I have to zoom out a bit. It occurs at 45. There we go. There's our sketch. State the domain and range. All right, domain and range. It's an odd degree function. That means the domain, all real numbers, and the range, all real numbers. Product and quotient of functions. Again, we're going to take the same functions, same f at x, same g at x, but this time we're going to divide f at x by g at x, and then we're going to sketch that. So this will look familiar as well, because we've already done stuff like this. X plus 3 over x squared plus 8x plus 15. It simply gives us a rational function when we put these together. And we know all about rational functions. I would recommend, we're going to use Desmos, but before I even do that, I'd recommend factoring the bottom. So we're going to get x plus 3 and x plus 5. That's what multiplies to give 15 and adds to give 8. So then we can do stuff like, okay, we can see that x cannot equal -3 or -5, because that's going to give us denominators that are, well, that's 0. We can't divide by 0. Then we're also going to see something interesting here. We're going to see that this x plus 3 on the bottom is going to cross out with this x plus 3 on the top. So this simplifies down to 1 over x plus 5. So this is probably a good time to graph it. We should be able to predict the graph here, though. Actually, before I go to Desmos, let's just do one more thing. Let's predict the graph. I predict vertical asymptote at -5. VA, vertical asymptote, x equals -5. I predict a horizontal asymptote at y equals 0, the x-axis, because it hasn't been shifted up or down. Remember, we can get the y-intercept by putting 0 in for x. So we're going to have a y-intercept at 0.5. So that's going to be very close down here, 0.5. And beyond that, we probably can expect it to go something like, whoops, not like that, something like this and like this. Although, let's actually see what Desmos says so we can make it a bit more accurate. Looks like we were right. To get another point that might be a bit easier, so at -4,1 it looks like, and at -6,1 I can put those points on there to help me draw my sketch. These points here. So now I see I have to go in very close to this corner, and then of course up. It's not supposed to back up. It should be getting closer and closer to the asymptote from every direction. Okay, there's our graph. Except there's one thing that's still sort of bothering us. What about this, or should be bothering us? What about x cannot equal -3? So that occurs here, right? Here's -3. Now I've drawn the graph and given a point for -3. Desmos did the same thing, and here's a little tip. Desmos isn't going to recognize this problem. Well, maybe it will. I don't think it will. Let's try graphing the original function, which was y equals x plus 3 divided by, nope, put brackets around this, divided by x plus 5 times x plus 3. That's what it looked like before I factored it and reduced it. Now they look exactly the same, the two versions, so I know that I factored things well, but what happens at x equals -3? That's problematic. Let's see if I can slide over here until... Okay, it does tell me that at -3 it's undefined. So again, we can use what we learned about holes and say, okay, it's getting closer and closer. It's not an asymptote here. It's just undefined. So actually there should be an open circle here. Desmos doesn't draw that, but there should be an open circle. That's how we have to interpret that. So I have to back up, get rid of this part of the graph, put an open circle where it would be, make the curve carry on, put an open circle there. That's a hole. The way I can tell a hole from an equation is if it comes from reducing. So if we go back to this part here where we had x plus 3 and over x plus 3, before we reduced it, we still had this restriction that x could not equal -3. Just because I crossed them out doesn't make that restriction go away. It's just that it doesn't create an asymptote, it creates a hole instead.